So hello everyone and welcome to NITA CP YouTube channel. My name is Akshat Kumar Verma and today we'll be discussing three problems of the Codeforces round 749 division plus division 2 based on Techno Cup 2022 elimination round 1. This was taking place simultaneously. So first we'll start with the first problem which is Wind-Bloom Ode. So let's first read the problem statement. So this is the problem statement. First we are given with a reference from a game. The gamers who already played this game will understand this one. So we have obtained the elegant bow known as the Wind-Bloom Ode. So inscribed in the weapon is an array of n is greater than or equal to 3 positive distinct integers. That is, there are different integers and no duplicates are allowed. So we need to find the largest subset that is having the maximum number of elements of this array such that its sum is a composite number. So a positive integer x is called composite if there exists a positive integer y such that 1 is less than y is less than x. So what it basically means is, and x is divisible by y, that x is not a prime number. So what is the definition of a prime number? That this number is only divisible by itself and 1. So we need to find a number which is also divisible by some other number y. So basically we need to make the sum non-prime. So if there are multiple subsets with this largest size with a composite sum, you can output any of them. Okay, we don't need to maximize or minimize it, we just need to maximize the size of the subset. So it can be proven under constraints of this problem. Such a non-empty subset always exists. Okay, we'll also try to prove this one. So we'll try to read the input after we see the code. While seeing the code, first we'll look at some examples. So this is the first example that we are given. Okay, so we are given 4 test cases. The first test case contains 3 elements which are 8, 1 and 2. So sum of this whole array is what? 11. Now 11 is prime. We can't output a prime number, we want a composite number. So we'll try removing one element. We'll remove this 2. We'll end up with 8 plus 1, which is 9. So 9 is not a prime number, it is divisible by 3. So we'll output that as our answer because that is the largest we can get other than the whole array itself. Now checking for the second case, which is 6 plus 4, 10 plus 9 plus 2, which is 21. So 21 is divisible by 3 and 7. So it is a composite number already. So we don't need to make any operations like remove any one of them. We'll just output the whole array because that is the largest subset possible, the whole set itself. So now we consider the third test case. So here also the sum comes out to be 9 into 10 by 2 and into n plus 1 by 2 formula. So which will give us 45. So 45 is also divisible by 3, 9, 5. Okay. So it is also a composite number. And we'll just output the whole array because it is the largest we can get. Similarly, you can prove for this one as well. So from these examples, we have seen that we will write this as the first case. Okay. So our first case comes out to be that if the sum of the whole array, is already composite. So if sum of the array is already composite, that is non-prime, so we can just output the whole array, right? As we have seen, because that is the largest possible. Composite means non-prime. So if the sum of the whole array is already non-prime, then we will output, then answer will be, we will write answer, and our answer would be whole array. So in this case, we'll just run a loop from 1 to n, and this whole, for outputting the whole array, we'll just output 1, 2 up to n separated by space. So this will be our answer for the first case where sum of array is composite. Now checking for the second case. The second case would be simply when sum of array is prime. There are broadly 2 cases. All the inputs can be classified into 2 cases. It will be either prime or non-prime. So we need to do is check for this case where sum is actually prime. Now we'll try to make some observations here. Okay. So we are given that n is always greater than or equal to 3 and then elements are always greater than 1. So the sum of the whole array will always be greater than or equal to 3, right? It can't be less than 3, and after 3 all the even number that will arrive cannot be prime, right? Because they all will be divisible by 2. So all the even numbers are actually non-prime except 2, and the sum is always greater than 3. So we know that this sum will not be even, this will be an odd number clearly. So this will be, sum would be odd. So we need to make one more observation here, that if the array already consisted of even numbers, for example say 2, 4, 6, then this sum can never be odd number. This will always be an even number. Why will this be an even number? Because if we take out common 2 from here, we're left with 1, 2 and 3. So this sum will always be in the form 2 into something something. So this will always be even. So sum of even numbers can never be odd. So from this we have proved that this array where the sum is coming out to be prime, this has to contain at least one odd. So this has to contain at least what? Has to contain at least one odd number in it. We can't make a odd number without with just even numbers, and we have already proven that this will not be even. So we need to make a odd number. For that we need to include at least one odd in the array. Okay, so if there is just one odd, uh, so we can just remove this odd. What will we get? Because this is another property that odd minus odd is always even. So you need to remember this for further questions as well. For different questions, this will be very useful for you. So we have already seen that a sum is prime and odd, and we need that array is already consisting of at least one odd. So if we just subtract the sum from this odd, we'll get with an even number, and the size of subset will be n minus 1, which is the largest possible after n. So it is done. A solution is made that in the first case, what we are going to do is, in the first case, if first case is that sum of array is composite. In that case, we'll just output the whole array, and in case it is prime, so we'll just remove one odd from it and output the whole array. So this was the whole solution. Now we'll look at the code. So this is the code that is submitted during the contest. Okay, so this is a function I made for checking whether a number is prime or not. It's a really optimized code because that does not check for each and every number, each and every divisor of it. It just increments by 6 because we're already checking for 1, 2, 3 here. So what is the input format? The input format is the first line contains the number of test cases. So we have taken in the test cases and we have run a while loop that will run while t is greater than 0. So this code will actually run for t times. For each test case, we need to input an integer n in the second line which contain n integers. So this is what we have done. We have first taken the input n, we have done a loop for n times. In this loop, I have done many things. Like first, I have already checked the sum of the array. So we don't have to another loop for calculating the sum. So initially, I have initialized the sum with 0 and kept on adding the array I, that is the input. And I have also made this as odd element, which is of no use actually, because we have already seen that if the number will be prime, it has to contain at least one odd. So this is not necessary. So now we'll check if the number is not prime. So I have added this condition that if sum is not prime, that is, it is composite. If it is composite, we'll fall in the first case. This is our first case. So if we fall into our first case, what will happen is we will just output all the integers. So first we have to output the number, the size of subset, and then we'll run a loop from 1 to n as discussed and see out end l. So this will make the first case, and this is the second case. Now for the second case, I didn't need to check anything. We could just delete this whole part. We could just go with the else condition. Now here I have added one bool done once. Now why I have added this done once? Because we have proved that it has to contain at least one odd. Now it might also contain more than one odd elements. So we don't need to remove all the odd elements. We just need to remove any randomly odd element, because it was mentioned that if there are multiple subsets with this largest size, we can output any of them. So if done once is false, initialize it is initialized to false, that I have not outputted any odd yet. So if done once is false and array I minus 1, that is the previous one, because I am running the loop from 1 to n. So if because this is 0 based indexing and the previous one is odd. So if this is odd, I will set this done once to true because I have already outputted a I have already skipped an odd element, and from the next time we don't need to skip, we will write all the odd elements in it. So this was the solution that got accepted. I hope you understood it. Now let's move on to the second problem, that is the problem number B, which is Omkar and Heavenly Tree. So you might get a bit overwhelmed by seeing all the problem statement in this, but trust me, this is not a graph or tree related problem. This is really simple problem. If you even know some basic concepts of graphs and trees, then you will be to understand this very easily. Now stay with me for some time and give your full concentration to this question. So Lord Omkar would like to have a tree with n nodes, n is greater than 3, and asked his disciples to construct the tree. However, Lord Omkar has created m restrictions to ensure that the tree will be as heavenly as possible. Right? He wants the most heavenly tree. So a tree with n nodes is a connected undirected graph with n nodes and n minus 1 edges. This is the basic definition of a tree. Note that for any two nodes, there is exactly one simple path between them. Right? For if we want to go from this node to this node, there's just one path. Right? There are no other paths to this. There are no cycles as well. This is the basic definition of a tree. And simple path is a path between two nodes that does not contain any node more than once. Okay, this is another definition. So for example, we need to go from here to here. We don't need to go through this node again and again. We'll just come from here to here. This is the basic definition of a tree. So a restriction consists of three pairwise distinct integers a, b and c. It signifies that node b cannot lie on the simple path between node a and node c. For example, if this is node A and this is node C, this cannot be node B. That is what this restriction signifies. So can we help Lord Omkar and become his most trusted disciple? So we will need to find heavenly trees for multiple sets of restrictions. It can be shown that a heavenly tree will always exist for any set of restriction under the given constraints. Now again we will try to prove this fact as we did in the last question. So we will read the input later. First we need to check what is the input given to us. So first we are given with two test cases. This is okay, so we need to read the input. First line contains n and m, size of tree and the number of restrictions. So the size of tree is 7 and the number of restrictions are 4. So the first restriction is that the path between 1 and 3 could not contain 2. The path between 3 and 5 cannot contain 4. Path between 5 and 7 does not contain 6. The path between 6 and 4 does not contain 5. So what do we need to output? For each test case, we need to output n minus 1 lines that are all the edges, number of all the edges. On each line, output two integers u and v, signifying that there is an edge between node u and v. Given edges have to form a tree that satisfies Omkar's restriction, that the tree is really heavenly. Okay, so this is the first tree. We try to see the example output. So for the example output, there is a node between 1 and 2, as we can see here. There is an edge between 1 and 2, between 1 and 3, 3 and 5. Right, this is basically the tree that is formed from the first equation. And you can see that it satisfies all the restrictions. The restrictions were basically that the path between 1 and 3 does not contain 2. So 1 and 3 are directly connected. 3 and 5 also does not contain 4. This is also directly connected. 5 and 7 does not contain 6. So the path between 5 and 7 is here, 5, 3, 1, 2, 7, and 6 is actually located out than this path. Then in the path between 6 to 4, we do not want 5. So this is the path between 6 and 4, 4, 3, 1, 2, 7, 6, and 5 is actually out of this path. So this is the basically example that we got. So we try to again make some observations here. Okay, we'll move to our whiteboard. This is the question we want to do now, Omkar and heavenly tree. Okay, so basically again we will make some observations as we did in the last one. So we are given that we'll check the constraints on m. Okay, so m is always less than n, right? It is not even equal to n. So m is always less than n. That is the number of restrictions. So if the number of restrictions are always less than n, that is number of nodes, we can safely say that there will be at least one node, right? If this is a, b and c, this is the input format. So if m is always less than n, we can safely say that there will be at least one node that does not appear even one time. It does not appear even one time in all the m restrictions in the between. That is, that node will have no restrictions whatsoever. So any path can cross through that particular node. Now why we can say that? Because if there are m restrictions, we will write m lines. We will try to, this is the first line, right? We will write second line, third line, fourth line. And even if we make everyone in every subset, we will make b distinct, like there will be b dash, b double dash, b triple dash. So here b are all distinct, and even then we will left with at least one node, right? We will actually be left with n minus m nodes. They are not coming even once in this restriction wala part. So we are done with the basic intuition part that was coming to me. Okay, this was the basic intuition that came to me, that there will at least be one node that will not appear even once in the restriction part. So what can we make of it? So I made of that this as well. Okay, we will not write it as one. We write it at a simple node which is x. Now this x is actually the node we talked about that is not coming even once in the B part. This is the input format, and this node x is not even in one of the restrictions. So what it means is, if it is not in any of the restrictions in the B format, so any path can pass through this x node. So what if I connect all the nodes from actually this node? These are all the edges. Okay, this is the first node, this is the second node, this is the third node, this is the fourth node. Now as you can see, this is also a graph, right? It does not contain any cycles, and every path will have exactly one element one time. This is a simple path between any two, right? And x does not came even once in this B. So we can safely say that this is the most heavenly tree we can form from it, right? This is the most heavenly tree. It will not contain any restrictions that are given by Omkar, and this safely satisfies the condition for a graph being tree. So this problem only boils down to one single thing that we needed to notice, that m is less than n, and if m is less than n, there will be at least one node satisfying this condition of this graph, that will make this as a center node and attach all the other nodes to this particular node. Now you might notice that there might be multiple nodes that might occur in B. So we'll just check which is the first one that is not occurring in the like B part, and we will connect all the other nodes to this node. So now we'll see the implementation. So this implementation is a bit mess because I made it during the contest only. So this is not at all needed. No graph functions or no graph we need to make at all. This is the input format. We first need to input the number of test cases t. That is what I did. And then for each test case we need n and m, number of edges and number of restrictions. Now this line is also not needed at all. We don't need to construct any graph in this one. So what I did now is that I made an array of length n and initialized it with 0. I will basically use this array for hashing. So see, what I did is I take input for all the constraints, because it was written that the next m lines will contain three integers ai, bi and ci. And what I did is A and C are of no use to us. As we have seen, we just need to find that one node which is not occurring even once in this B part. So A and C are of no use to us. We don't need to actually retain it or process it from any kind. So we'll hash it. I have hashed it like array b minus 1 plus plus, that this node has come once or anytime more in the B part. So we'll just increase the count of it from 0 to 1. And for now we'll iterate to 1 to n, and if we find an element which has not even occurred once in this B part, we'll store this in the index variable that I have made and break the condition here, because that's all we need. We just need one node which has not even occurred once. So now I will again iterate from 0 to n, right? And for every I will just input idx1 and I plus 1. So this basically means that we needed to output u and v, right? That signifying that there is an edge between nodes u and v. So this index is basically the x node that we talked about. This is the x node that we talked about. It is stored in what? Index variable that I made. So it is stored in the index variable, and we will just make edge from this x to each other one of the nodes. So that's what we did. We made an edge from this to every one of the other nodes, and we just not make an edge to itself. We don't want like this, because this will not be a tree. This is a graph, but this will not be a tree. So if idx is equals to I, we'll just skip that case. And this also, you can see that this loop runs for n minus 1 times, like excluding this. So we have outputted n minus 1 lines for each one of them. So this was the solution for B problem. This was a pretty easy problem, I must say, because there were no graph concepts involved in this one. So now we'll move on to the C problem, which is Omkar and determination. Now this was a really interesting problem. Let's read the problem statement first. So problem statement looms below filling you with determination. Sure, definitely. So consider a grid in which some cells are empty and some cells are filled. Call a cell in this grid exitable if starting at that cell you can exit the grid by moving up and left through only empty cells. Okay, so we are given a grid. For example, we'll move to the third one. We might be given a grid like this, right? We are given a grid like this. Okay, and in this one, some of the cells are filled, like for example, this must be filled, this is filled, and all the others are empty. So we call a cell exitable if from that cell, for example, if we are checking for this cell, we will be checking for this cell, we can move up and left and exit this grid. So we can just move left, 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 left from here, and we can exit this grid. Right, let's make a filled one here, and let's check for this particular cell. Now from this cell, I cannot move up and I cannot move left. So this cell is what? Non-exitable. This is non-exitable. Okay, I really like this pen. So this cell is non-exitable. This cell is what? Exitable. So the exitable part must be clear to us by now. So this includes the cell itself. So all the filled cells are non-exitable, obviously, because we cannot move anywhere from this cell. So this cell is always non-exitable, the cells which are already filled. Okay, so now note that you can exit the grid from any leftmost empty cell in the first column by going left, and from any topmost empty cell in the first row by going up. So for each of these cells, which are marked right now, we can just move up from here and exit the cell, and we can move left from here and exit the grid, not the cell, exit the grid, but we can't exit from these two. So this change in statement was actually made during the contest. This was not written, leftmost empty cell was not written, and this changes was made actually during the contest. So we'll call a grid determinable if given only which cells are exitable, we can exactly determine which cells are filled and which are not. So we are given not with this array. If we are just told that this cell is exitable, this is not exitable, we can make the whole grid but determine that which cell is filled and which is not. So we will call that grid determinable. For example, if this grid we are just given that the first is exitable, 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 non-exitable, exitable. So like this, if we'll be given, we'll be able to tell that if this grid is determinable or not. So what is a determinable grid? That from this matrix we can make this matrix. That basically means determinable matrix. So we're given a grid A of dimensions n cross m, that is a grid with n rows and m columns. You need to answer q queries. Each query will contain two integers x1 and x2 and asks whether a subgrid containing of the columns x1, x2, x1 to up to x2 is determinable or not. Okay, so we'll be given just one grid in, and we will need to answer q queries format. Q queries will actually contain, for example, say this is x1 and this is x2. So we'll need to tell whether this subgrid, like not containing this one, so we'll have to tell this whether this subgrid is exitable or not. So that is what the question basically states. So input format is we will take in two integers n and m, the dimension of the grid A, then n lines follow. Okay, this is basically the grid. Then we'll take in the queries. So output format is output one line containing yes if subgrid specified by the query is determinable and no otherwise. So the output is case sensitive. Okay, no need of reading that. So this is the grid that is given to us. This is empty, empty. These are all are filled. So a dot basically represents that this cell is empty, and x means this cell is filled. So we are given with 5 queries. 5 queries are as follows. We first need to check for the first and the third column up to here. We need to check for this whole up to down. Okay, so we are given with the really awesome explanation for this. We'll check this, read this once. So this is the array, this is the grid that has been given to us. This is second one, and we need to determine this. And if we can determine this one array, this grid from exitable and non-exitable one, then we will say that this grid, this subgrid is actually determinable and output yes. Okay, so if we'll try to make executable and non-executable grid from this one, we'll end up with this, that the first cell is executable. This whole column is actually executable. We'll just move one left from it. This whole column is again executable. We'll move two times left from it, and except this whole column is also executable. This is just non-executable one. So if we are given with this grid, we can easily determine that only this one is the filled cell, and all the other must be empty because they all are executable. So if they're not executable, they might be non-filled, they might be filled, but since they are all executable, there must be an empty cell. And this one is non-executable, so we'll just output X from there. So we have seen this from second grid, we can actually generate the first grid. So this subgrid that was from 1 to 3 is actually determinable and will output yes from it. Now let's check for an example where it is outputting no. So no is coming in 4 to 5 subgrid. 4 to 5 subgrid means we'll check for this column and this column. So here is the where is the fourth and fifth column, right? Okay, this one. This is the third query. This is the fourth and the fifth column. So for each of these, you can see that none of the cells are actually exitable because these all are actually filled. We can't exit from there, and these all are actually we can't move left from it nor up from it. So this cell is actually non-exitable, and from this cell also we can move up, but we'll actually end up with this X with this filled cell. So this is also non-exitable. Similar is the case with this one, and we can't move left from it as well. So what happens is we come up with this one that all the cells in this grid are non-exitable. Now I need to make you an observation. Now if this we are given that is non-exitable, so this cell can contain either X or this dot. Why? Because we don't care if this is actually filled cell or an empty cell. Even if it is a non-filled cell, that is an empty cell, we can't exit from here because on moving up we'll encounter an X, and from moving left we will encounter an X again. So this cell will never be exitable. It does not matter it contains X or a dot. So this cell is actually not determinable. If we are just given that this cell is non-exitable, we can't tell. We just can't tell that whether it is filled or not filled. And that was the definition of being determinable, that we must be able to determine that whether a cell is filled or not. We can't do this for this one, and neither for this one, neither for this one, because these three can either be filled or not filled, but they will always be non-exitable. So we have made a very good observation here that if a cell is non-exitable, then we don't care whether we don't care whether it is a dot or an X. That means whether it is exitable or non-exitable. So this will be our actually algorithm. First we will take another example as well to check this no condition again. So we are given with 1 to 5. It is the whole grid actually. So for the whole grid we can make this grid that these cells are exitable. Definitely these all cells are exitable. This is again exitable, and these all are again exitable. All those marked with X are filled, so they are non-exitable. And these we have already seen we can't move anywhere from them. We can move up from these two, but we'll finally encounter an X which will be of no use to us. Okay, so from this cell again, these three cells we just can't determine because they're non-exitable, right? Because they're non-exitable, and we just can't tell whether they will contain a dot or an X. So again, here's the same observation that we made, that if the grid contains a dot, that is if a grid contains a cell which is not filled and which is non-exitable, then in the grid which will be determining whether it is exitable or not, it will just contain an N, and from this grid we will not be able to make out that whether this cell was filled or not. So what we need to check is that if any of the grid contains even one non-filled cell which is non-exitable. Non-exitable means that it cannot move up or it cannot move down. For these cells we will not check, we will just check for this one single, because obviously we can assume that these these cells are exitable. If we assume that these cells are exitable, then moving up, we'll make a contradiction here that no, this cell is not actually exitable. So then there must be another cell which is not filled and non-exitable. So we'll just ignore these two one. So what we'll consider is in each grid we will try to find a non-exitable cell in which the above character format is x and the left character format is also x. So if we find even one cell which is not filled and uh, what should I say, and satisfying these two conditions that both of them are x, then we'll just make a check variable, bool variable or anything. We'll set it to true and we'll output false for that subgrid. I need to make you again, I need to listen to this again. For each subgrid, we need to check this condition. So I actually checked for this one and this gave TLE. So we can't actually like brute force this solution, right? We are given with 2 seconds and the constraints are really high. N and M and Q are 10 to the power 6 and 10 to the power 5. So we can't brute force the whole solution. So what comes to our mind when we can't brute force the whole solution? So we have to actually process the single grid for different queries. For this types of questions, all most of the time we need to use pre-computation type of things. We need to pre-compute that which are exitable, non-exitable, these types of things. So that's what we will do. We'll try to pre-compute. So what will we pre-compute this time? We'll pre-compute the prefix sum. Okay, we'll pre-compute the prefix sum for this grid. So what will that prefix sum actually contain? So let us move on to the third question. This is the third question only, sorry. So we'll make an array, a prefix sum array of size m. This will be of size m, okay. Now what will this contain? This will basically contain that which cell that if that column, will make this of size m, that is it will have the it will have some value for each of the column. Now for each column we'll input here how many cells are there which are non-filled, that is there is a dot and which contains x on both of their sides. We don't actually need for dot. If even if there is an x which contains x on its top and x on its left, will contain non-exitable on its other grid, and we can't determine whether it is a x or a dot in the original grid. So we'll just need to check that if there is any one of them in this whole column, any element in which the top element is x and the left element is also x. So obviously you can check from here that we can't check for the first row and for the first column. We'll not include this. We'll roll this from the first row and the first column, that is from 1 comma 1. And for the first column we can safely say that there will be all exitable, that is will be all determinable. All the cells will be actually determinable. If there is a non-exitable, then we'll input an x, and there is non-exitable, we'll put a dot there. Okay, that is quite simple, right? Okay, so the first one will always input 0 in it, and on the second one we need to calculate the prefix sum. So if this contains 1, and in the third column we come to know that there are three cells which satisfy the condition, then we will not put 3 here, we'll put 4 here. And if this column we come to know there are 5 cells satisfying this condition, then we'll put 9 here. So in this way we'll make our prefix sum array. Okay, in this way we'll make our prefix sum array. Now how are we going to use it? So basically for each subgrid we need to check that whether it contains all the cells which are determinable. So in the prefix sum we are actually storing cells, number of cells, I must say, number of cells which are non-determinable. We are actually storing what? That number of cells in that column which is not determinable. So if for two integers, let's say, we'll just zoom out a bit. Okay, so in this prefix sum array we are actually storing the number of cells in that column which are non-determinable. So for two integers x1 and let's say x2, okay, for two integers x1 and x2, this is the ending row, this is the starting row. If the number of cells between these two elements, for example, let's say the value of, we'll call it pre array. So the value of pre for x2 minus 1. Why I'm selecting 1? Because it will be 0 based indexing in this array, and our integers given to us are in actually 1 based indexing form. So we'll check that if pre in x2 minus 1 and pre x1 minus 1 is actually equal to 0. Now what does this condition mean? This condition basically means that the subgrid between x1 and x2 does not contain even one cell which is non-determinable. Only then will be the sum equal. For example, let's consider here that in this row we find out that there are 0 elements which are non-determinable, 0 cells which are non-determinable. Then we just input 4 here. So if the sum 4 minus 4 is 0, that basically means that this subgrid does not contain any cells which are non-determinable. Pretty simple concept, right? We need to implement just this. So we'll run a loop for each queue time. We'll take in x1, we'll take in x2, and we'll check for this condition that pre of x2 minus 1 and pre of x1 minus 1 is 0 or not. If they are 0, we'll output what? We'll output yes in this case, else we'll output what? No. Pretty simple implementation. Okay, now we'll check for the submitted code that I made for this question. So we'll first input this two integers that are given to us. I will open the question again. So we first need to input two integers n and m. Okay, then n lines follow. We'll just take in the grid. Okay, we'll take in the grid again. See, this is the where I made the character array for this grid because we are containing with x and dots. And this is the pre-sum array that we talked about, prefix sum array. Okay, now as we talked about that the first grid will not contain any element on its left. So if it will not contain any element on its left, then how will we check for this condition that if this is our element x, then here should also be x and there should also be x if this is our element. So we can't check for this condition because there are no left elements. So we'll always make the zeroth column 0 value. Now this is the running count that I will use. Running count means the number of cells which are non-determinable till now. Okay, so I will run this loop from 1 to m because as I have discussed already that for the first column we'll just input 0. Okay, now this loop will run from first row to the last row. Why? Because again in the top row we can't actually check for the above element. Okay, so we'll run this loop also from the first row to the last row. So in this whole column we'll check that, okay, let's check this condition very carefully, that array I and j minus 1. So what does j minus 1 mean? That if this is the grid, let's say, okay, this is the grid, this is our grid, and we're checking for this element. Now I represents the rows, this is I and this is j in its increasing order. This is the arrow. Okay, let me go there. This is I and this is j, and we are checking for this element. Now what I have written is array I and j minus 1. What does j minus 1 mean? We are going one above, that is we are checking if this one is x or not. Second condition, array I minus 1 j. What does I minus 1 mean? We are checking if this one is x or not, and if these both are x, we'll say that this cell is non-determinable and we'll increment the count, and for each j I will put the count there, and you can see this is a running count. I don't set it to 0 in every loop, so this will give me the prefix sum as discussed. And then I will input the number of queries. I will run a while loop like we ran in the test cases in the previous two questions, and then we'll input x1 and x2, and we will check this condition that we just saw, that pre-sum x minus 1 minus pre of x minus 1 is 0 or not. We'll check for this condition everywhere, that pre-sum x2 minus 1 minus pre-sum x1 minus 1 is 0. And if it is 0, then we can say that this subgrid does not contain any cell which is not determinable, and if it does not contain any cell which is not determinable, then the whole grid is actually determinable. We'll see out yes, or else we'll see out no. So this was it, guys. This was all for this contest. Now if you have any problem, feel free to note it down in the comment section or ask in the NITA CP group. Also, please give your feedback whether you want these kinds of video, that all the solutions will be in one video, or you were better liking the previous format, which was all the videos were divided into 3 parts. Now before ending, I would also like to just tell you a glimpse into this one C problem. Now for this C problem I also made two submissions. I'm just telling this because, just a second. For C code C, once I made the two times same submissions. One took 1279 milliseconds and the second one took 155 milliseconds. Now this is a lot of improvement, isn't it? So what I only did was, you can check in the two solutions. The only difference is I've included two lines here. See, it is starting from LLN or M, and here I've included these two lines. Okay, this is for the fast input output, and this is the optimize the code by a lot of time. See, you can say by, I don't know, 10 times or something. No, not 10 times, but all right, you get the idea. That is, it reduce the time complexity a lot. So for these kind of problems where you have to take in a grid and where you have to answer multiple queries, always try to use these two lines for fast input and output methods. This also gave TLE in my previous attempts during the contest. See, I was given TLE on many times. Wrong answer also I got. So always try to use these two lines. Thank you guys. This was it for the video. This is Akshat Kumar Verma signing off.